So on to oxygen, which is our third gas of the gases we have to look at in gas chemistry. Obviously a very important gas in terms of life on Earth and also for chemical reactions as well. Just as a little aside on the name, we talked about hydrogen, how hydrogen is named after the fact it makes water, so hydrogen, water maker. Oxygen is quite interesting in that it's actually named incorrectly. The scientist who discovered oxygen and named it was a French scientist called Lavoisier. He thought that oxygen was the key element that made acids acidic. So when he called it oxygen, oxygen actually means acid maker. So we've since learned that it's not oxygen, it's hydrogen that makes acids acidic, but the name stuck, so oxygen is actually named incorrectly. It means acid maker. But anyway, on to the key facts. First of all, its formula, it's O2, so it's another example of a diatomic gas. Should be quite familiar with that. Its physical properties, again, these are very reminiscent of the physical properties of the other gases in this topic. It's another colourless, odourless gas. This second point is accidentally migrated in this document. It should be a use, so we'll talk about it later. The proper second point is it's slightly soluble in water. Now that is a little bit of a contrast. Both nitrogen and hydrogen don't dissolve in water. Oxygen doesn't dissolve that well in water, but does a wee bit. One key fact that sort of backs it up, if you think about fish breathing underwater, they need oxygen. But obviously they don't come up to the surface to get the oxygen. That kind of proves that oxygen actually is a little bit dissolved in water. So they're able to pick up oxygen from the water that they're swimming in, and that gives them the oxygen they need for respiration. It's also a neutral gas, so even though it is dissolved in water, it doesn't affect the pH. So 3 physical properties for oxygen. Next bit's the preparations. Remember, preparation just means how do you make it in a lab. What we use for oxygen is a bit of a strange reaction. We haven't seen this before. What we use is a chemical called hydrogen peroxide. Hydrogen peroxide is the formula H2O2. So it looks a little bit like water, but with an extra oxygen. Hydrogen peroxide is a strange chemical in that it will actually break itself down to make water and oxygen. So it's not a very stable chemical. And that equation looks like this. Now, in normal circumstances, that will happen over the course of a few weeks. So if you leave some hydrogen peroxide out, it will gradually break down to water and oxygen. Obviously, in experiments, we want that to happen a wee bit quicker. So what scientists use for this reaction on top of the hydrogen peroxide is a catalyst. It's a very specific catalyst. It's called manganese 4 oxide. Its formula is MnO2. So if you add manganese 4 oxide to hydrogen peroxide in a flask, it'll very, very quickly start bubbling. And the bubbling being produced is the oxygen gas being given off. So that's the basis of how we make this in the lab. How we collect the gas is again by downward displacement of water, like we saw for hydrogen. So just seeing this diagram here, it looks a little bit different, but same idea. You got a flask, there's your hydrogen peroxide, the liquid there. Hydrogen peroxide is just like a liquid like water. We've got little granules of manganese 4 oxide, remember that's just a catalyst. Starts bubbling, starts making oxygen, that goes out to the delivery tube and then to a beehive shelf and a gas jar filled with water. The oxygen will bubble through the water up to the top, start pushing the water down as it takes its place, and you'll end up with a gas jar just filled completely with oxygen. Once you've got the oxygen, you might want to test it's actually there. So we've got our test for oxygen. Hopefully you should remember this from down the school. If you add a glowing splint to oxygen, so a glowing splint is one that's been lit but just blown out, so still kind of glowing red but not actually on fire, it will relight in oxygen. Oxygen is the thing that makes things combust well. So if you put a smouldering thing into pure oxygen, it will come back to life, the flame, and start burning again. Uses of oxygen, again, obviously we use it for breathing, but in terms of like actually industrial sort of society uses of oxygen, there's a couple maybe to know about. I don't know if any of you have been scuba diving, but scuba diving involves using oxygen in a cylinder, which you will breathe in through a wee breathing apparatus. So it allows deep sea divers to go for long periods of time underwater. Similar idea if you're in hospital. So if you're on a ventilator, that's oxygen being pumped into your lungs for you. So again, that requires oxygen to be bottled and supplied to you. Another use is this use down the bottom left here. That's a welder. Now, welding, hopefully you should know, is when you are basically fusing two metals together. That involves having a very hot temperature to basically melt them in a localized area. The hot temperature comes from basically a flame, And the more oxygen you have in the flame, the hotter it will burn. So we use what's called Oxy Acetylene Welding. Acetylene is the fuel that burns, and you pump in oxygen with that fuel to burn it really, really hot. So essentially oxygen helps you to weld things together. So those are the two uses in the notes. So welding is properly called Oxy Acetylene Welding, but basically it's using oxygen during the welding process. And then the second one is breathing apparatus for deep sea diving or for hospital patients. So our last little section on oxygen is about kind of the chemistry of oxygen. Oxygen is a very important element in chemistry because it makes oxides. So whenever you burn something, in other words, chuck something in the Bunsen burner, it's going to be reacting with oxygen in the air. So it's a very, very, very common reaction to carry out. What we've got in the notes here is the reactions of 5 specific elements with oxygen that Sia asked you to kind of learn off. It's to try to prove that basically lots of things react with oxygen. In other words, oxygen is quite a reactive gas. So they picked a sample of 5 random elements just to kind of study their observations and their equations. Now, 3 of these you have done before, 2 of them are a bit new to you. So the 5 elements we've got 2 non-metals, we've got carbon and sulfur, they're on the right side of the periodic table. Then you've got 3 metals, magnesium, iron and copper. So we'll break it down in chunks. The first thing to worry about, we'll come back to the observations in a second. First thing to worry about is what you make. So if you burn carbon and oxygen, you make the gas carbon dioxide. If you burn sulfur in oxygen, you make another gas that's called sulfur dioxide. If you burn magnesium in oxygen, you've guessed it, magnesium oxide. Iron will make iron oxide. And copper will make copper oxide. So that's the first thing to kind of establish. You're making a compound which has the element first, you're burning, and then oxide at the end. With carbon and sulfur, you get 2 oxygens forming a bond, so it becomes dioxide. Second thing to look at would be the equation, just to kind of chunk it up. Carbon with oxygen is not too complicated in the equation. So it's just carbon plus O2, remember it's diatomic, goes to CO2. That's actually all balanced as it is. Sulfur, very similar. Sulfur's S, reacts with O2. Sulfur dioxide's got 2 oxygens, so still SO2, just as you'd expect. Then we got onto the metals, which involve a wee bit more balancing. Do bear in mind that these reactions did actually come up in the reactivity series. You looked at the reactions of metals with oxygen. But anyway, so magnesium reacts with oxygen, it'll make magnesium oxide. You can swap and drop that, Mg2+, magnesium group 2, oxygen's group 6, that's going to make just MgO. Balancing it needs a 2 in front of the MgO and a 2 in front of the Mg. Iron is a standout weird one. If you remember back to the reactivity series, it forms what we call a mixed oxide. It's helpful if you just remember that the oxide you get with iron is Fe3O4. If you remember that, the rest of the equation becomes relatively simple. So Fe plus O2, we'll need 3 Fe's and we'll need 2 O2's to make 4 oxygens there. And the final one, copper, Cu plus O2. Remember, looking at the back of your periodic table, you'll see that copper is 2 plus. O2 minus, swap and drop, just going to make CuO, and we just need a balance there and a balance there. So equations, just like you kind of expect, just the element plus oxygen, you're going to make from some sort of oxide according to a swap and drop. Then we'll look at the observations. So we'll start with the ones you're more familiar with. So magnesium, iron and copper, this is just taken straight out of your reactivity series notes. So magnesium will burn with a bright white light, produce a white ash or white solid at the end, which is magnesium oxide. Iron, you might remember, makes the sparkles. So if you have iron filings in a Bunsen burner flame, you'll see orange sparks and the iron will turn black. Then copper is the one that doesn't actually go on fire, it just kind of glows red, but you form a black layer of copper oxide at the end. The 2 new ones are this carbon and sulfur. So carbon, just imagine like a coal fire. So it burns with an orange sooty flame and it forms a colourless gas, just like burning coal in a fire. Sulfur is the standout one. This is the one where there's most detail and it's most new, and to be honest, probably most asked of all the observations. There's quite a lot going on here. Sulfur is a yellow solid, so it's a very vivid kind of canary yellow colour. When you heat it up, it melts first. So before it starts to burn, it melts. When it melts down, it darkens a wee bit, so it goes to a red liquid. So yellow solid melts to a red liquid first. Then it starts to burn. We see another colour where it burns. The flame it burns with is blue. So the red liquid has a kind of blue flame on top of it. And what you produce, sulfur dioxide, is a colourless gas, but a very smelly, pungent gas. So as you can see, here's quite like an observation dense kind of reaction here. Yellow solid melts first to red liquid, burns with a blue flame, and the gas given off, sulfur dioxide, is a colourless, pungent gas. So that's observations, products, equations. We've got this strange column here, nature of oxide. You might be wondering what that is. Another point we're trying to prove here is that whenever we talk about acids and bases, as we talked about in year 11, something we didn't really touch on is kind of what types of compounds become acids, what types of compounds become bases. We did talk a wee bit with the bases, with hydroxides and oxides. But one general trend is that when you have a metal oxide, so in other words a metal reacted with oxygen, they will generally form bases. It also is true of hydroxides, but oxides first of all will form bases. And non-metal oxides, this is a bit new, they'll form acids. Now, it's a little bit complicated here because if you think about carbon dioxide and sulfur dioxide, they're gases. You might think, well, how could that be an acid? What we're really talking about here is if you took the gas and dissolved it in water, you'll make an acid. You might remember us talking about in acids or the fact that fizzy drinks are acidic, because when you dissolve carbon dioxide in water, it turns into carbonic acid. Same here, SO2 dissolved in water will make something called sulfurous acid. So lots of acids come from non-metal oxides dissolved in water. So don't worry about that too much, don't get too bogged down. What I've just written there is kind of the key trend. You could be asked in the exam to predict if they gave you another element oxide. So for example, aluminium oxide, that would be a metal oxide. You'd have to know it's a base. So just that key kind of pattern here. So carbon, it's a non-metal oxide, it's going to be acidic. Sulfur dioxide, non-metal oxide, will also be acidic. Magnesium oxide is a basic metal oxide, so basic. Iron oxide is also metal oxide, so it'll be basic as well. And copper oxides is also a metal oxide, so it'll be basic as well. So metal oxides are always bases in water, non-metal oxides are always acidic in water. Little kind of extension question here, how could you test to see if you had acidic or basic oxides? Not too complicated, all you do is dissolve them in water, because that's actually proving if they are acidic or basic. And test with a universal indicator and just check the pH. So that's what we need to know about those oxides. Just keeping track of what we got to. So oxygen is kind of normal gas, O2 is colourless, odourless, does dissolve in water, it's neutral in water though. And we make it from hydrogen peroxide with a manganese 4 oxide catalyst, and we trap the gas with downward displacement. We test that gas with a glowing splint relighting. We use oxygen for welding and breathing apparatus like scuba divers or hospital ventilators. And oxygen is a very important element in chemistry because it reacts with lots of things. We've got 5 elements just as a wee sort of sample of those reactions. 2 non-metals, carbon and sulfur, and then 3 metals, magnesium, iron and copper. We looked at the equations, looked at the observations. We saw this kind of new thing where this pattern where metal oxides tend to be bases in chemistry, non-metal oxides tend to be acidic. So we can categorize and maybe predict any other ones based on that pattern.